Fair warning. Recording is on.
Recording is on.
Today, Bruce, honestly, today, it's not the day for joking around because if we get lost today, it's going to be a mess. Okay? So, with that being said, calendar. I updated the calendar yesterday based on what we did yesterday and what we didn't do and blah, 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 blah. So, yesterday, we talked about some acceleration concepts. I have acceleration homework review. That was basically the conceptual side of acceleration. We talked about is this acceleration, is this not acceleration, blah, blah, blah. Then, towards the end of the period, we started getting into the relationship between velocity and acceleration. And that was the problem set that we started working on yesterday that we will continue working on today. Okay? Like I said, today we're going to talk about the relationship between velocity and acceleration. We will talk about the incline a little bit more. That's an object rolling down the ramp. And then also we'll see how far we get, but we may get into some free fall, and we'll talk about that at the end. Okay. Tomorrow, we will continue on that relationship, but now instead of things just going down the ramp or falling down from a tall ledge, we're going to go up and down. Talk about how the acceleration of that object is there, etc., etc. Okay. As far as the schedule goes, Friday, next quiz is scheduled, okay, based on the things that we've done over the past couple of days. I'm planning on having it at the beginning of class. You come in, you take the quiz. Then the remainder of that period, we will work on our next lab, but we're going to collect data together because we don't have block this week, and we're on short periods next week, and so it'll just go faster if we collect data together. With working on these two things together, we could probably get the data collection done in about 20 minutes. That'll be good, and we'll work on it next week. As far as the test goes, right now, tentatively, I have the test. Right now, tentatively, I have the test scheduled for Thursday of next week, but we talked about the idea that we may have to break this test up over a couple of days because we're on short periods next week, or depending on how far certain things take us, we might end up pushing it back to Monday of the following week anyway. So, yes, sir.
Okay, so like a long test.
It's maybe not as long as the test you just took, but it will be, a decent amount of points. That's why we may break it up over 2 days because of the fact that we're running into OGTs and stuff like that. So,
Do we have an outline for what we're
objectives?
not like don't or is this?
Oh, we're still working off of that outline.
Okay.
So yeah, we're still working off of our same outline. Yeah. I haven't posted the objective sheet yet. So give it a couple of days. All right. Good there?
Yeah.
Here we go. All right. Over the past couple of days, Monday, we introduced the concept of acceleration. And we said, by definition, what is acceleration? By definition, what is acceleration? Austin, go ahead.
The rate at which velocity.
Good. The rate at which velocity changes. Okay. And we said that because that's the rate at which velocity changes, this is our formula for acceleration, right? That A is equal to delta V over T. The delta representing the change in velocity over the time. That's going to be an important thing we have to keep in mind as we go forward here. Acceleration measures the change in velocity. Okay? Physically, we talked about 3 things that can be considered acceleration. 3 physical motions that are acceleration. One, speeding up is one kind of acceleration. Next year. Slowing down is the second kind of acceleration. Changing direction is the third kind of acceleration. Okay? We talked a little bit yesterday that the changing direction part really comes in when we talk about things in 2 dimensions, like going around a circle and stuff like that. Okay? Today, and for the next couple of days, we're going to be exclusively in 1 dimension. So we're just going to be dealing with the speeding up and slowing down part of acceleration at this point. Okay? All right, are we good there? Yesterday, I believe we did the top part of this problem set, is that correct? Where we first talked about the non-accelerated motion. If something is non-accelerated motion, what is that telling you? Say.
If the velocity isn't changing, so it stays.
Good. The velocity isn't changing, or we would say that the velocity is constants. Okay? And the way that showed up was in this, we talked about that if we took a picture of this ball rolling at a constant velocity, right? That if it goes 1 meter, right, in a 1 second time interval, that in the next second, how far should it go? It should go 1 meter, right? And that in the following second, right, it should go again another meter, right? And then in the following second, blah, 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 right? That we end up here, that interval for how far it travels each second remains the same. Okay? Good there. All right. Then we got into the beginning of accelerated motion. Is that correct? We started off just a little bit. Okay. All right. Let's pick it up there. First, we have an object rolling down this ramp, and it is undergoing a uniform acceleration, which is another word for a constant acceleration. First thing I want you to do in your small groups, discuss what does it mean if we say something has a uniform or a constant acceleration. Talk.
It means it increases in speed by a certain
What's the amount of what? We'll go over here.
Is it by, I do believe naturally it's because it speeds up at constant intervals.
All right. So let's discuss. Miriam, is it okay if you answer the question for us? Because I know that we discussed it. So the fact that something has a uniform acceleration, Miriam is going to tell us what about that object? It increases. What increases? The velocity, or we could say the speed in this case. So the velocity increases by the same amount each second. Okay? Because remember we discussed that acceleration, here, let me do this, let me get myself, okay, here, grab this, then new sheet. We talked about the idea that acceleration is equal to the change in velocity, right? So if we have a uniform acceleration, that means that its velocity keeps changing by the same amount each time interval. Okay? Good there. Okay. It's only like the first of 15 times I'm going to say that today. That acceleration is the change in velocity. All right. For this ramp specifically, it told us that the acceleration was equal to 2 meters per second squared. Okay? With that being the case, we said that 2 meters per second squared, we could rewrite that in a couple of different ways to maybe make it a little bit more descriptive as far as what's going on. Right? So we said that we could rewrite that as 2 meters per second, or, and the way that I think is maybe the most descriptive as far as telling you what's going to go on, right? If we go 2 meters per second for every 1 second, right? All these are equivalent ways of writing 2 meters per second squared, but they might tell you a little bit more information. Okay. Did we get to the actual numbers on the ramp yesterday?
Yeah.
Okay. If we start this object at 0 meters per second, not green, if we start this ball at 0 meters per second, okay, and it experiences a uniform acceleration of 2 meters per second squared, that means that its velocity is going to change by 2 meters per second for every second that goes by. Yes?
Yeah.
So that means that after 1 second, if this ball, if each of these pictures represents 1 second worth of time, right? After 1 second, that object is going 2 meters per second. Okay? Then we said in the next second, this would be 4 meters per second, 6 meters per second, 8 meters per second, and then 10 meters per second. Are we good there? Okay. That handles the how fast part. Now, we handle the how far part. This is where things get a little bit more confusing. So, with that being said, let's focus in on one little section of this right here, and that being just this little section right here. Make it a little bigger so we can write on it. Okay, notice in between the 0 second ball and the 1 second ball, what does it tell you about how far that object went?
1 meter.
1 meter. I would bet a lot of money. There's at least some of you that are sitting there going, wait a minute. The next velocity says 2 meters per second. Shouldn't that mean it goes 2 meters?
No, because it has
9
accelerate.
so it's
Wow. That being the case. Wow. We didn't go over that yesterday, did we? Okay. Fair show of hands, right? Okay. All right, here. Fair show of hands, okay? How many people are sitting there thinking right now, okay? Be honest. This says 2 meters per second here. So shouldn't this say 2 meters, that the ball went 2 meters during that time? Okay. All right. I know that you guys aren't the only one, all right? But fair show of hands, all right? That's one of the traps that people fall into, okay? Because it says, well, wait, it says 2 meters, right? And remember back here on this picture, right? This was a constant velocity. It went it was going 2 meters per second. Well, this was only going 1 meter per second, right? But it went 1 meter, 1 meter, 1 meter. Okay. Well, we said that each of those balls represented 1 second worth of time. So we do know the time. Okay. But here's why that's not the case. Okay, Alex, what did we say what's going on here?
Well, it starts at rest and it kind of has to get to that speed. It's like when it kind of goes 0 to 60 and then stays at 60. It has
Okay. If this object, or if the ball was going 2 meters per second the whole time, then it would travel 2 meters, right? But what has happened to that ball between here and here? It's gradually speeding up, faster, 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 faster. When's the only time that it actually gets to 2 meters per second? At this point right here. That's the only time it's actually going 2 meters per second. The rest of the time it's going what? It's going slower than 2 meters per second, right? Because it has to build up to 2 meters per second. Does that make sense?
It's going slower than
During this red squiggly part, right? From here to here, right? It's going slower than 2 meters per second because it only gets to 2 meters per second at that point. Okay.
3 meters per second.
Now, same with this. Okay. During, let me get a different color here. Okay. During this purple section, right? Faster, 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 faster. But it only gets to 4 meters per second right there. That's the only time it's going 4 meters per second. The rest of the time, it's going faster than 2, but slower than 4, right? It's building up to get up to 4. Alex, go ahead.
Wouldn't it be per 2 seconds because that's the second ball?
No. Yeah, it is the second ball, so that's 2 seconds after it started. But if I look at the purple section, right, this represents 1 second worth of time because it goes from this ball to that ball.
So when it's like only from ball to ball.
Right, each ball represents, like, it would be, Alex, if we took a picture every second, that's where the ball is at those consecutive second times, okay? All right, now, let's start talking about where this number comes from, okay? Parker, go ahead.
Is it the average between the two velocities?
Good. On average, right, we know that at the beginning of this red interval here, okay, how fast is the ball going at the beginning of that red interval? 0. And at the end of that red interval, it's going 2 meters per second. Parker, if we look at the average during that time, right, to calculate the average of anything, just math-wise, right, what do? Add everything up and then divide by the number, right? So if we look at the average velocity during this interval, okay, we only know 2 velocities, the beginning velocity and the end velocity, right? If we add those 2 together, let's start it at 0 meters per second, and then it ends up at 2 meters per second, so that's a total of what? 2 meters per second. How many velocities did we add up? Just 2, right? So that gives us an average velocity of 1 meter per second.
Where'd you get the 2 meters per second from? Just the speed?
That's the speed it was going at the end of this little red interval, Alex. Okay, does that make sense? Now, Alex, if we go back to something that you said, I think you said it. I wanted to ask you this question. Okay, yeah. We said that here, this red interval represents how much time?
Oh, 1 second.
1 second. Okay? On average, during this time, it was going 1 meter per second, speed or velocity.
Oh, and that would be over 1. So.
If it was on average going 1 meter per second for 1 second worth of time, how far did it go in that interval? 1 meter. Does that make sense? Okay. Now, don't get confused. Does that mean it was going 1 meter per second during this entire interval? It actually was only going 1 meter per second for like a split instant. But half of that time it was going slower than 1 meter per second, and the other half of the time it was going faster than 1 meter per second. So on average, it averages out to 1 meter per second. If that average of 1 meter per second occurred over a time interval of 1 second, we went 1 meter. Okay? Is that good for starters?
Yeah.
Okay? Okay. Let's do this. Let's do the purple next, and then we'll see if that answers some questions.
I just have a question.
Sure.
So it's like after the 1 meter is traveled, then it starts going 2 meters per second.
At the end, yeah, Pierce. After it has traveled 1 meter down the ramp, if we clocked its speed, it would be 2 meters per second. But only at that point. The rest of the time, it hasn't gotten there yet. Okay. Here, go ahead. Okay. Well, let's talk. Let's do the purple one. I think it might. As we do a little bit more, I think it might start making a little bit more sense. Okay. Alex, go ahead.
In this case, what would be the initial? Would it be 0 or
No.
would it be the 1 meter?
The initial velocity is 0.
No, but what you're trying to find the velocity. In this case, because you need to change distance, or do you not need to?
Remember, we're talking about average a little bit, right?
But yeah, that's change over time.
Yeah. So if we did this, we would see that we went 1 meter in 1 second. So we'd say its average velocity is 1 meter per second. But that's not how fast it was going, right? It was actually speeding up.
No, I meant from the 4 meter distance, which would
No, don't go to the 40 meter distance yet. Hold on. Don't go there. All right. Let's look at the purple. I'll walk you through another one. Okay, so let's go with the purple. Okay. If we take this, we do exactly the same thing we did. Discuss in your small groups, what is the average velocity going to be during this time? Go.
3. It's because the average of 1 and 2 is 3.
So 4 equals 6 divided by 2 equals 3.
Wow, that's right.
It's kind of complicated to think about it. Like it's not one thing.
I might know like what to
Okay, let's discuss. Okay. Now, during the purple interval, that's all we're talking about now, from this location to this location. Okay? If we talk about the average velocity, right? We know the velocity at two locations. We know the velocity at this ball here. We know the velocity at this ball here. Oh, not that. Here. Right? It started off going 2 meters per second at this location. It ended up going 4 meters per second at this location. And we know that from the acceleration values. Just finding a quick average of those two values gives us 3 meters per second. Is that good?
Yeah.
Okay. Tim, is that good? Now, Tim, I heard you kind of talking a little bit about the plus versus the minus,
Yeah,
right?
that was
Yeah. Just got to keep that stuff straight, right? We're not calculating the acceleration now. We're calculating what the average velocity was during that time. Alex, how much time has gone by during this purple interval? 1 second. So if we've gone an average of 3 meters per second for 1 second, right? That means that how far did we go during that 1 second? 3 meters.
So that means the initial would be 1.
Now, if we were calculating the average velocity here, right? It's gone through, we're just looking at this little section, right? It only went 3 meters during that little section. So that, if we're calculating the average velocity, that's what we would use just for that point there.
And in this case, would it always be like that? For
Yeah. All right, are we good with that so far? Okay, here's what I want you to do next. In your small groups, okay, I want you to calculate for me this distance, and this distance.
Average velocity.
I want you to calculate the individual distances of those little trips. Okay?
No, question. Yeah.
Four, six, that was actually 5 meters per second.
Right, but given that, could you just figure it out that way? You could, yeah. Although that only applies like to specific situation. We're gonna give you even more general.
it's confusing when you're trying to think about it. Like,
It's confusing what?
I need to
if you're trying to like actually like think about it,
All right. So if we look up on the board, right? Okay. First, during this interval, right? From here to here, right? Initial velocity 4, final velocity 6. So on average, how fast was it going during that interval? 5 meters per second. How many seconds go by during that interval? 1 second. 5 meters. 7 meters, 9 meters. Anybody not see where I got that from?
Aren't you just like finding numbers that add up to the next square?
I mean, kind of, but that's what that's what we see out there in nature. Is that's how it works. Okay. If let's take a big picture view here. Okay. Let's take a look at. Let's see what color I'm going to use here. Yeah, we'll go orange again. Okay. Let's take a look at this whole trip. Okay? If we apply what we just talked about to this entire trip, Okay. What is the average velocity for the entire trip? Like 5 meters per second. If we look at the entire trip, I started at 0 velocity. I ended at 10 meters per second velocity. The average during that time would be what? 5 meters per second. Now here's where it gets a little tricky. Okay, the same thing we were just doing, right? But now I'm not looking, here, let me do this and see if this works. Right? I'm going to basically, I'm starting at 0, but I'm not looking at everything in between, all right? So I'm going to basically block out this section here, okay? And here, to do that, properties, it's stuff with like more than I needed to do, but whatever. Yeah. Okay. I'm just taking it all away. Okay? So I'm just giving you that. From that, do you see where the average velocity during this time is equal to 5 meters per second? Right? It starts where? 0. It ends up at 10. 0 plus 10 is 10. Divided by 2, which is the average. Because, right, so it's just, there's still only 2 points. Now, make sure you're on a roll here. Okay. Now, how long did we say that trip took to get down the ramp? It takes 5 seconds. So if we go an average of 5 meters per second for 5 seconds, how far do we end up going?
25 meters.
Okay. So Caroline, we're doing
I know you multiplied.
Caroline, we're doing exactly the same thing we did for these individual intervals. Okay? Except if we're talking about this whole trip now, we can't just multiply the average by 1 second, because it didn't take us 1 second to go down the ramp. How long did it take to go down the ramp?
Oh, I get it. I think I was thinking about it. Yeah, I understand what you're saying.
All right, are we good here?
Yeah.
Alpha,
So
go
wait,
ahead.
So like when you asked to find like the distance between like the intervals, that is going to average velocity.
During that interval, okay, if I ask you to find like the distance for the ramp, then I'm talking about a bigger time interval. Okay. So let's do this, okay, before we do questions, okay? Let's go here. On the bottom of that page, okay? On the bottom of that page, there is another ramp. Okay. Let me grab it here. That is a constant acceleration. It's just the acceleration is different now. So here's what I want you guys to do. I want you to find for me, what are the velocities at these different intervals? There's still 1 second intervals. Okay, so I want you to find the velocities. Now the acceleration is 4 meters per second squared. Then I want you to find how far does it go in each of these little intervals. Okay? And then, some way or another, I don't necessarily care how, I want you to find out how long the entire ramp is. There's a couple ways you can do that. Okay? So, I know most of you have started, and that's okay. Remember, we said if the acceleration is 4 meters per second squared, that's the equivalent of 4 meters per second for every 1 second. If you want to work together, perfectly fine. Alright? I'll start writing answers up on the board here slowly so you can see how you're doing. Go. If you're not sure how to get started, go ahead and talk to somebody. I want you to find the individual velocities in each of these points, then the distance that they travel, and then I want you to find the whole distance. That's what I want out of you.
Yeah.
it'll be easier. It's easier to see physics when I type these colors. So.
Oh, hey, wow, I already got that part right.
Problem subwards.
Oh wow, that's what it
That means way
was.
hard. That means that you have to start doing these calculus.
See, I don't get why would the first part be 4? On the last one it's 4.
Because what is the initial velocity?
Oh, and then afterwards.
1 second later, it's got to be good. So this is actually the ramp distance, right? Even though it's exactly the same ramp.
Yeah, I know. No.
That's 50.
I don't know how they do it.
Any of it?
Oh, no.
Okay.
I got the other stuff right.
So, let's discuss. Alright, let's discuss. Hey, we're just about to wrap this up.
50? Oh, isn't it 5 seconds? Yeah, where's the
No, that's meters per second.
Oh,
Sorry.
okay.
So, yeah, that's 20 meters per second. Alright, so let's discuss. Because the acceleration is 4 meters per second squared, right? That means that the velocity is going to change by 4 meters per second for every second that goes by. So if we start at 0, the next 1 second later it's 4 meters per second, 8, 12, 16, 20. Good there? Then, so the first interval, right? 0 meters per second at the beginning, 4 meters per second at the end. The average velocity is 2 meters per second during that time interval. That means that if it's 1 second worth of time, 2 meters. Okay, then 6,
Is that all it's
10, 14, 16. Or 14, 18. Okay? Is that what?
no.
Now, 2 ways that you can find this, the 50 meters. What's one way you could do it? Just add all of them up. Okay? The other way you could do it is if we look at the ramp as a whole. Right? The average velocity for the entire ramp is equal to 10 meters per second. And I got that because it starts off at 0 and it ends up at 20. But time-wise, how long does it take to get around the ramp? 5 seconds. So if you're going to an average of 10 meters per second for 5 seconds, that means the ramp is 50 meters long. That's all. We said each ball represents 1 second worth of time, right? So this is 0 seconds, then 1, 2, 3, 4, 5. Okay. All right.
Which ones do you add? You don't add, you add the yellow ones, right? Not the
Yeah. If you're looking for the distances, you're going to add distance numbers, right?
Yeah.
All right. Now here's kind of important parts. All right. We're going to wrap this up. So pay attention here. Okay. These relationships get summarized with mathematical equations. That's what physics does. We take observations of what we happen, or most, at least mechanics-wise. We take observations of what we see and find the pattern, and then mathematically model that pattern. So, 2 equations that we get out of today's work. The first equation looks like this. Okay? First equation looks like that. Bf is equal to Vi plus A times T. Okay? Everything that we just talked about conceptually gets summarized by that. Well, not everything, but half of the stuff we talked about is that would summarize the pattern of the red numbers here. Okay? Now the next one's a little bit more complex. Okay? Just the t is squared there, not the whole quantity. Yeah, just the t is squared in that equation, not the whole quantity.
Hey, it's up there.
And if you're astute, right?
Well,
Pay attention to what's going on. Okay.
it's on the wood thing.
It's done with it too. All right. These two equations summarize pretty much everything that we talked about today. Okay? For homework tonight, I want you to do the back of that problem set. There is another ramp up at the top. Then the next one is an object falling through the air. If you read the little description at the beginning, you'll get the acceleration value. All right? Got your homework for tonight is the back of this page, which looks like this. Okay? One more ramp and then a free fall problem. So if you read the problem, you'll get the if you read the little description, you'll get the acceleration. All right? Good work today, everybody. We'll continue on tomorrow.
Starting out with what's the goal?